This video is going to talk about extensive forms or game trees, and a little bit about how to solve them using something called backwards induction. So here I've drawn a game tree up on the board here. This would be a game version of something called a money tree game, and then you think of this money tree could actually end up being part of a game sometimes called the Centipede Game. And the idea of the money tree is that there are two players playing this game, and they're going to start with money in a bowl between them. And the players have the option to take, they're going to take turns, and what they can say is, I want the money, or they're going to harvest the money, like, let's take the money. Or they could pass on their turn, or let the money grow, in which case the other person then gets to choose, and the second person then would choose to either harvest the money, like take the money out of the bowl according to a given division of it, or leave it in there, and in which case it would go back to player one, and player one would get to make a decision about whether it's keeping it in the bowl or letting it grow, keeping it in the bowl or harvesting it. And so the idea here is, like, maybe this could be done as an experiment with a experimenter, like say me running the experiment and two students, and we'd be putting money in a bowl in front of them, and every time that they choose not to end the game, I would be putting some more money in there, and then in effect the total amount of money that they'd have would be going up. So the way I've got it set here is that it'd be like, say, $5 in the bowl to begin with. If player one says on their first move, let's end the game, the player one gets 80% of the money that's in the bowl. If they pass, or if they if they keep the money in the bowl, which is what I'm referring to as grow here, then another $5 gets added to the bowl. So there'll be $10 in the bowl. Player two then has the option to say stop or harvest, in which player two, if player two exercises that option, player two would get 80% of the money that's in the bowl, 80% of $10 being $8. And if player two chooses not to harvest, then player one would get the remaining $2. And then if player two chooses not to harvest but keeps the money in the bowl, player one gets to make the same choice. And as long as these players keep saying, let's grow the money in the pot, the amount of money will be increasing there. So this could be an example. What would be a real world example of this is that, say, suppose two people each had the opportunity to use some kind of a resource, like, say, this could be like a forest or orchard of trees, or that you could be allowing to grow. And the more time you let the stand of trees grow, the bigger they get, and the more timber you have there, and the more valuable they'd be. But you have the opportunity to come in and cut them and sell them and get the money. So this would be referring to a case where you're trying to cooperate to grow something together, but either player could be ending this. Well, the point of it with a game tree is that in some ways it's going to look pretty similar to a decision tree that you might have seen in other contexts. But the point of a game tree is a situation where there'd have to be at least two people who control nodes during this tree. So if this was a decision tree and there was only one person who was making the choices at any point in this tree, or in this situation being modeled, then it's a decision tree. When two people are making choices at different points in here, then it would be a game tree. So the situation I've described is one where the players where there's two players, and so this would be a game tree. Since there's more than one player involved here, one of the things you have to do is you have to indicate in the tree what player is making a decision at what point. So there are three different decision nodes. The decision nodes here in this case are the big dots, the larger black dots that I've drawn in here. And you can see that as I have it set up here, player one gets to choose, and then player two gets to choose, and then player one gets to act. So player one's going to act twice. If you were actually running this game as an experiment, you could let the players go on trade back and forth many times. I've only got room here on this board to show a couple moves, so we're only going to have three moves here. So a game tree has nodes, and then they have branches. And then at the end of a game, you have what are called terminal nodes. When there's no more moves for anybody to get, for anyone to take in the game, then you've reached what's called a terminal node of the game. So you have branches, you have nodes, decision nodes, branches, and then at the end you get to terminal nodes. Every terminal node of the game, well, you have to. Every terminal node of the game is a type of outcome. So you want to be able to then say, well, what payoffs do the players get here? And so I put the payoffs here in little brackets. And the convention would be that the payoff for player 1 comes first, and then the payoff for player 2 would be second. So it would be 4 and 1 here, 2 for player 1, 8 for player 2, and so on. Okay, so this is the structure. Now, it's actually, there's a way that economists like to use to think about a strategic choice in this game, and that's what's called backwards induction. So you go to the end of the game, and you work backwards to figure out what does rational choice mean at each point here. So, this player 1's second move here would be the last choice in the game. If player 1 reaches this node and has to make their second choice in the game, they have a choice between harvest and grow. Now, with backwards induction, we're relatively straightforward because what we're going to apply here is say, let's assume that the player chooses the action that gives them the higher payoff. So very straightforward. If player 1 was to get here, then comparing these two options, harvest gives them a payoff of 12, grow gives them a payoff of 4. Well, 12 is bigger than 4, so player 1 would choose. That's a marker that's going to work here. Player 1 would choose harvest if you reach that node of the game. Okay, and I put a couple of arrows on there, but again, it doesn't look like the orange is showing up so well on this. So now you can really act as if now we're going to consider player 2's choice, and player 2 can really act as if player 1 doesn't have a choice. By a backwards induction, given what we have determined here, it's as if player 2 knows that 12-3, this payoff here from harvest, is really the payoff he is going to get if this node of the game is reached. In reality, we know player 1 has to make a choice, but via backwards induction and looking to see if player 1 has to move in this case, what would player 1 do? And restricting the player 1 to choose the strategy that would give them the higher payoff would really allow us player 2 would know that if they choose grow, they're going to get 12. It's going to be 12 and 3, and their payoff is 3. So it's as if, I don't want to redraw this here, but it's as if you could eliminate this choice node for player 1 and just tag this, bring this payoff up here. Now player 2 is choosing between this. They realize they get 3 because that's their payoff here, or if they choose harvest, they get a payoff of 8. So backwards induction says that a player at the next to last time a player is going to move in the game, again, apply this same thinking. Player 2 would be comparing 3 and 8, and the higher payoff is 8, so they would choose harvest. And then, so really this would be the payoff that would apply here for this, with backwards induction. It's as if we've turned this node into a terminal node of the game, because by saying like we have this and then this, we know that this is really the payoff that the players would get if we get to this node in the game. So now we can look at player 1's choice between, well, this payoff and this payoff. So it's 4 versus 2. And, well, 4 is bigger than 2, so player 1 would choose here. So we've now, through backwards induction, laid out the entire play of this game. And it comes out that each player would choose to harvest their money tree here, end the game and get the money out of the bowl. and whenever they got a choice. So in equilibrium, we would see, well, player 2 would never get to move because via backwards induction, we figured out player 1 should rationally end this game with their first move. Now, that's this just as a we're spending just 3 class periods on game theory here, so we can just touch on this. But this shows, in some sense, although we think that backwards induction is a good way to think about rational choice in games, this also shows something of a weakness of this, that that some game theorists would look and say, like, well, does this really make a lot of sense? Because as this goes on, players are getting better and better payoffs if they allow the resource to grow here. And you could continue this on with more choices than this. Like I said, I just ran out of space here on the whiteboard, so I just had growing it 3 times. If you get it enough times to grow, then you get a payoff down here where both players would get a bigger payoff than what they had to begin with. So some people would argue that although, yes, there's this logic to backwards induction, and you're going to start at the end and say, if player 1 gets to move here, we're going to assume that they're going to do what's in their rational best interest. And then via that reasoning, work backwards and see that something like this is going to lead to harvest immediately. At the same time, you sort of see well, you might say, and especially the more times this is going to grow, does it really make sense to kill this goose that's going to lay all these golden eggs in the first time? Now, again, the way we've got set up here with backwards induction is suggesting that yes, you should do that. But for that, this is kind of an interesting question, but it's one that's going to be beyond the scope of what for us to really get into in this class. This is just a taste of what we do with game theory. Is what we're doing in these 3 class periods that we're covering it. So you'd have to study some more game theory to actually get into thinking more about a paradox like this. But this is backward induction and how we would apply it in a game.